Today we'll be discussing on Thevenin and Norton equivalent circuits. They are part of network theory, and whenever we talk about Thevenin and Norton equivalent circuit, we are dealing with one port network, and one port network is a network that has only one pair of terminals. So for example, if we have a linear network, so let's say this is a linear network, and this is a port, basically two terminals where we can connect any load, such as the terminals ports coming out of our utility. Those are considered one port network. So let's say the voltage V is given here, and then the current is I, and this kind of networks will have voltage and current characteristics. So they are characterized by the current voltage relationship. And usually the linear network, such as the electricity that is coming to your house, is a complex network, and it is possible to simplify these networks using the concept of equivalent circuits. So this lecture and next few lecture will rely heavily on this concept of equivalent circuit, which is equivalent circuit. Any complex one port network, may be replaced by an equivalent consisting of a source and a resistor such that the current voltage characteristics at the terminals are the same. And there are two different types of equivalent networks. One was introduced by scientist Thevenin and the other one by Norton, and they are called as Thevenin equivalent and Norton equivalent respectively. Let's get started with the Thevenin equivalent. So this linear circuit, which has one port, can be written as Thevenin equivalent, having a voltage source with VTH and a series resistor with the resistance value of RTH or Thevenin resistance. So to solve this kind of problem, we evaluate these 2 points, once using open circuit approach and then using the short circuit approach, and we calculate the VTH and RTH. So we evaluate 2 convenient points to show they are equivalent. So those 2 points are open circuit and short circuit. Okay. So case 1 with open circuit. So we have linear network, and since this is the open circuit, the voltage can be written as V is equals to VOC, open circuit voltage, and since this is open circuit, the current is 0. So because whenever we mean open circuit, we mean there is infinite resistance, and in terms of current and voltage, it means current is equals to 0. And this is equivalent to the Thevenin voltage, VTH. And if we look into this circuit, if I is equals to 0, and if the voltage across this open source is VOC, we see that VTH is equals to VOC because the current is 0, so across this RTH there is no voltage drop, so VOC is equals to VTH. So when we start trying to form Thevenin equivalent, we will have to determine the open source voltage of the original network, and that will give you the Thevenin voltage. Okay, so for further analysis, we need to look into the short circuit condition. Second is short circuit. So in the short circuit, from the electrical perspective, we know that voltage is 0, right? So in the linear network, let's say this is our one port and we short circuit this. Okay, so across this short circuit, the voltage is 0, and then the current is the short circuit current, and this was our linear network, and this will be equivalent to here is the resistance. Let me erase it and redraw it. Okay, this was RTH, this was VTH, and the current I is the ISC, short circuit current, and the voltage across these two open port is 0, V is equals to 0. So in that case, how can we determine RTH? We know the voltage is VTH from the open circuit condition earlier, and if we can decide the current ISC, short circuit current, then we can use Ohm's law and determine the RTH is VTH divided by ISC, right? So that's the Thevenin equivalent. And there is a Norton equivalent which was developed by other scientists. Norton equivalent. In Norton equivalent, it's basically practical current source. So it's a parallel combination of current source and a resistor. So this linear network here is equals to a current source which is in parallel with a resistor. So we call this resistance as Rn, and this current is In, Norton current and Norton resistance, and this is the linear network. Okay, so I'm skipping the derivative right now. We just have to keep in mind that In will be equal to the ISC, the short circuit current we calculate in the earlier case, and the Norton resistance equals to Thevenin resistance is equals to VOC divided by ISC. So if you recall from last lecture on source transformation, this will look like something like this. So we have RTH, we have voltage source. So between these 2 points you have VTH, which is basically the practical voltage source, right? And if we look into this, this is Rn and this is In. So this is the Norton equivalent, right? So we can see in this case that, let me use a different pen to draw right this ones. So VTH is equals to RTH times In, and RTH is equals to Rn, if they are equivalent, right? So if you relate this to voltage and current source transform, so what it looks like is the voltage to current source transform is equivalent to Thevenin to Norton equivalent, right? Norton equivalent transform. And similarly, current to voltage transform is equivalent to Norton to Thevenin equivalent. ENE equivalent. Okay, let's look into a practical example, and we'll see how we can calculate the equivalent of the one port network. Okay, here is the example question, which is asking us to find the Thevenin and Norton equivalent of this one port network. And here is the network that I'm going to draw. Okay, we have a current source which has 15 ampere, and we have a one port A and B. We have another resistance here and one resistance here. Okay, so this is 8 ohms, this is 2 ohms, this is 12 ohms, this is 10 ohms, and let's say the current flowing here is Ix. So these are two open outlet here, so this and this, they are two open outlet, right? So that is, they are one port network, and hence we can use the Thevenin and Norton equivalent circuit. Okay, one thing we know is the Thevenin voltage is equal to the open source voltage of the original network. So if this open source voltage VOC, then the Thevenin voltage is equals to VOC. And now we have done so many different circuit analysis techniques in this class. What would be the best way to do circuit analysis to find VOC in this case? We could use node voltage method. We can also use mesh current method, but the simplest one is the current division rule, because we can simply find Ix using current division rule, and VOC is basically parallel to the this resistor, so the voltage drop across this circuit will be equal to VOC, right? So let's use that, and using the current division rule. Ix, which is the current flowing through the 12 ohm resistor, is given by Is, which is 15 ampere, the source. And then we have 1 by 24 ohm. Basically, this current coming from here branches out to this part and this part. In this part, we have this 1 resistor, 2 resistor, and 3 resistor. So that will be this, that the path the current is flowing. So that is the, sorry, that is the resistance there, 1 divided by R equivalent of this side, divided by 1 divided by 8 plus 1 divided by 24. Okay, and that will give us 3.75 amperes. Therefore, we can calculate VOC as Ix times 12 ohm is equals to 3.75 times 12 is equals to 45 volt, and we know that open circuit voltage is also equal to the Thevenin voltage, right? And the second condition was determining the ISC using the short circuit condition. So in the short circuit condition, you have this 15 ampere, and basically we're going to sort this part. Okay, okay, so this was our 2 ohms, this was our 10 ohm, we had 12 ohm here, and we had 8 ohm here. So now we are short circuiting between points A and B. The current ISC flows this through the short circuit, but then since there is short circuit, the current bypasses this resistance. So this resistance is of no use, or you can just calculate the parallel resistance between this element and this element, is basically 0. You get 0. So to calculate ISC, we can again use the current division rule, right, and calculate that one. One thing to keep in mind is that when you are doing the second step of the Thevenin or Norton equivalent circuit, don't use the values that we calculate, like current and other values we calculate from the earlier case. We just calculate VOC by open circuiting the circuit, and then that is the Thevenin voltage. And for the short circuit condition, we have to do everything from scratch. So now this is gone. We can use the current divider rule again, right? So current division rule again, ISC will be 15 times, now we have only 2 resistors in series here, 2 and 10, that will be 1 by 12 ohm and divided by 1 by 8 ohm plus 1 by 12 ohm. This is 15 ampere. Okay, and if we do that, we are going to get 6 ampere. Okay, so that is the value of the short circuit current. Now that we know short circuit current, we can calculate the Thevenin resistance, which is equal to the Norton resistance, and is given as open source voltage divided by short circuit current. Now open source voltage was calculated to be 45 volts, and ISC is 6 amperes, so that will give us 6.5 ohm. So once you have the answers, the best way to show your answer is to draw the equivalent circuit. So I'm going to draw that here. So Thevenin equivalent here, and then in this side I'll draw Norton equivalent. Okay, so the Thevenin equivalent will be this, where you had the one port A and B, and your this is your A and B, and this is your RN, your IN, your RTH and VTH. Okay, so RTH was calculated to be 7.5 ohms and RN is equals to RTH, which is 7.5 ohm, and your VTH was calculated to be 45 volt, and IN is the short circuit current, which was calculated to be 6 ampere. So this completes the problem. We can use source transformation again to solve the same problem we did earlier, and then we'll see the Norton to Thevenin, which is basically current to voltage and voltage to current transformation. Let's do that using source transformation method. Source transformation for the same problem, okay, the earlier problem, which was this is 15 ampere, this is B, this is 8 ohm, this is 2 ohm, this is 10 ohm, and we had one more resistor here which was 12 ohm, right? So what we can do is we can convert this part of this part of the circuit, which is practical current source, in this case Norton equivalent, to Thevenin equivalent or practical voltage source, right? If we do that, what it becomes is this part remains same, right? So this is B, and this is replaced by a resistance in series with a voltage source, right? And since the direction of the current is leaving this side, so the positive terminal is upper side and the negative terminal lower side, this resistance is always equal to this resistance, so it will be 8 ohms, and voltage is basically current times the resistance, which is 15 times 8, which is 120 volt. Now we have elements in series, right? So these, now if we have voltage and resistors in series, we know from source transformation lecture that these can be added up together, right? So from these two we get this. Now from this we'll go down and to convert this into a single voltage source, because we only have one voltage source, and we have 3 resistors which are in series. So 8, 2 and 10 is 20 ohms, right? And we have we had the resistance which is 12 ohm, okay, 12 ohm. Now what we can do is we have this part with practical voltage source or Thevenin equivalent. We can transform it to Norton equivalent again and see the final transformation. Okay, so what we're going to do is we're going to convert this part into Norton equivalent or current source form. Okay, that will give us something like this. Okay, that will give us, so A, B, this 12 remains here, this transforms into a resistance in parallel and a current source. Since the positive terminal is in the upward direction, the current follows this direction. This is 20 ohm because the resistance remains same, and the current is basically voltage divided by the resistance. So 120 divided by 20 is 6 ampere. And now we have 2 resistance in series and 1 current source, so this can be reduced to something like this: A, B, and this is 6 ampere, and we'll get single resistance here, which is the parallel combination of these 2 resistance, 12 and 20. So 12 times 20 divided by 20 plus 12, which is 7.5 ohm, and we reach the same solution as the Norton equivalent circuit here. So this part here is same as the solution we got here. So different methods of solving the same problem. Okay, there is another alternative method to find our Thevenin or Norton equivalent circuit, Norton equivalent resistance, and this is helpful to cross-validate your work. One word of caution is that this alternative method I'm going to show is only valid for circuits that contain independent source. So let's see what is this. Alternative method for finding RTH is equals to R Norton. Okay, this method will be helpful, but again, this is only valid for circuits that have independent sources. So if you have dependent source, we have to find another method, which we'll discuss in after a few time, maybe after a few pages here. So the alternative method is first you zero the sources. So you zero the independent source. In doing so, what you do is, if you have a voltage source, we replace it with a short, replace by a short, which is basically voltage is equals to 0, right? And if you have a current source, we replace by open circuit, by an open circuit, which is basically current I is equals to 0. Okay, and once we do that, we find the equivalent resistance from one port perspective. So the equivalent resistance from the one port perspective equals Thevenin resistance or Norton resistance. So going back to the problem we had here, so this is our original problem here. In this case, we have the current source, so we are going to replace it with open circuit and look for the equivalent resistance from this side, the one port side. Okay, so let me redraw that. You have A, you have B, in between those we had this 12 ohm resistor, right? And we had 2 ohm resistor here, 10 ohm resistor here, and we had another resistor here which was 8 ohm, and we had a current source right here. But now, because we have current source, we are going to open circuit it to find the R equivalent, and you have supposed to find R equivalent from this perspective, okay, and R equivalent will be equals to the Thevenin or Norton resistance. And in this case, we can see if we start from this side of the circuit, current divides from, let's start from this point, so current divides this part of the circuit and this part of the circuit, and everything here is in the series. So 2, 8 and 10, they are in series, and the combination of that is in parallel with 12 ohms. So 2 plus 8, 10 plus 10, 20 parallel 12, which is 7.5 ohm. So, and that is the resistance we got from the above case. So this is a way to validate your answer. Okay, let's do another example for the Norton and Thevenin equivalent circuit. find the Thevenin and Norton equivalent of given one port network. And one port network is a network which has two terminals open. Okay, so let me draw this first. Say this was 1 and we had a voltage source, and this is B, and it's connected by another resistance here. So this is given as 72 volts, this is given as 20 ohms, this is given as 5 ohm, this is given as 12 ohms, this is given at 8 ohms. And now because we have this open port, one port, we can apply we can transform it to Thevenin and Norton equivalent. Can we apply a source transformation to this circuit? So one thing to note that these resistors, these are not directly in series, so there is another branch coming from this 5 ohm. So the 5 and 12, they don't, 5 ohm and 72 volt, they don't make a practical voltage source or Thevenin equivalent source. So we can do source transformation directly here. So what we can do is we can solve for this open circuit voltage here. Say this is the open circuit voltage using other methods we have discussed so far, and one of the easiest method will be node voltage. And we discussed different methods, right? Node voltage and node current are two of them, and I mentioned the steps to determine which one to use, right? And between node voltage and node current method, our idea is which one has the lower number of unknowns, right? So let's check for that. Actually, this will be good practice to do that. So let's assume I'm gonna use node voltage method. So if I assume this as the reference node, Vref is equals to 0, right? This voltage will be 72 volt, right? And we'll have two nodes of unknown quantities, let's say Vx and Voc. Okay, so we have two unknowns, and let's say we decided to do mesh current method. Okay, we had one current here, let's say I2, and then we had other current here, I1. Okay, again two unknowns. So if they have same number of unknowns, the second step, look for what is the desired quantity, right? And since here voltage is the desired quantity, node voltage method is preferred method. If you are looking for current, then mesh current would have been the preferred method. So we'll stick around with node voltage method, and let me get rid of the mesh circuits I made here. Okay, so now we have two independent nodes, right? And that's why we'll have to write KCL, right? So before that, we have to arbitrarily assign the current direction. That was our second step, right? So let's assign the current directions like this, and this. These are random directions, you can assign any way. And once you assign the current direction, use passive sign convention to write the polarity of the circuit. Now let's go back and write KCL at the nodes, right? So we have two independent nodes. Write KCL at node X, right, which is here. So we have one current source coming and the two leaving. So this current can be written as, since this is the positive terminal, it can be written as 72 minus Px divided by 5, right? That is the current flowing here, which is equals to the current across this circuit can be written as Vx minus 0, because this is 0 ground, divided by 20. And similarly across this is Vx minus Voc divided by 8 ohms. That was our second step of using node voltage method, writing KCL in terms of node voltage, right? So 72 minus Vx divided by 5 is equals to Bx divided by 20 plus Bx minus Voc divided by 8. Okay, so again this current enters here, leaves here, leaves here. And if I'm simplifying this, I will get something like 15 Vx minus 5 Voc is equals to 576. That is my equation 1. And we can apply KCL at the other unknown independent node, so which is this point. Let's call this point as A. Okay, so we can apply KCL at node A, and at node A, what we have at node A, we have one current entering from here, and we have other current entering is this one, right? If this is 72 and this is VOC, so we have two currents entering. So let's write that, and just to look back into this, 72 minus VOC divided by 12 volt, that is one current. Let's randomly assign the direction here too. That is one current entering, and then we have another current Vx minus Voc divided by 8. So both are entering the circuit, right? So as we know, we can assign random or arbitrary direction to the currents here. So 72 minus Voc divided by the 12 ohm resistor plus Vx minus Voc divided by 8 ohm resistor is equals to 0. If I am to simplify this, I will get 3 Vx plus 5 Voc is equals to 244. That is our second equation. Now we have two system of equations and two unknowns, so we can solve and get the values of Vx and Voc. So if you solve it, you will get Vx is equals to 60 volt and Voc is equals to 64.8 volt, which is equals to Thevenin voltage, right? And if you recall from the previous example, the second step is to find the short circuit current. So we'll have to short circuit this given example, right? So this example, we'll have to short circuit this and close the loop. So let's do that. Let's find ISC, short circuit current. Let me redraw this circuit again so that it's not too confusing for you guys. This is the part that was short circuited, and we had two resistor here and one resistor here, and this source was 72 volts. This is 12 ohm, this is 5 ohm, this is 8 ohm, this is 20 ohm. Okay, what would be an efficient way to find the value of the current ISC? We can do current source conversion, but then again, as I mentioned earlier, this is not in the practical voltage source, so we'll probably have to do delta to Y transformation between these delta circuits, which will make things complicated. The other option is to use node voltage method, but as I mentioned earlier, since our interest is finding ISC, we'll have to do KVL after node voltage method. So in this case, the mesh current method will be more efficient. So let's try mesh current method here. So let's assign the current here. Let's say along this loop I have current I1, along this loop I have current I2, and along this loop this current will be equals to ISC, because that's the short circuit current, right? So SSC, and we can start writing KVL around the mesh. Okay, let's write KVL around mesh 1. So if we do that, what we are going to do is get is minus 72 plus 5 times I1 minus I2 plus 20 times I1 minus ISC is equals to 0, right? That is one equation. If we simplify it, we'll get something like 25i1 minus 5i2 minus 20isc is equals to 0. And then writing KVL around mesh 2, we'll have 12i2 plus 8i2 minus isc plus 5i2 minus i1. Okay, so KVL around mesh 2, 12i2 plus 8 times i2 minus isc plus 5 times i2 minus i1 is equals to 0. We can simplify and we'll get 5 minus 5i1 plus 25i2 minus 8isc is equals to 0. So let's say this is equation 2 and this is equation 1. And now we can apply KVL around mesh 3, which will be 20isc minus i1 plus 8isc minus i2 is equals to 0. So this one is even easier. KVL around mesh 3, 20isc minus i1 plus 8isc minus i2 is equals to 0, or minus 20i1 minus 8i2 plus 28isc short circuit is equals to 0. So now we have 3 equations and 3 unknowns, so we can solve for the unknowns and we don't have to calculate all the currents, we just need isc. And if we solve this, we'll get isc is 10.8 ampere. Now we can calculate RTH is equals to VOC divided by ISC. VOC was calculated to be 64.8 volt, and now we calculated this as 10.8 amperes. That will give us 6 ohm, right? And we also mentioned about verifying RTH using the alternative method. Let's go ahead and do that. So in this method, in the alternative method of, where is the original circuit? So this is the original circuit. In the alternative method, we know that if we have voltage circuit, we replace that with short circuit, right? So we'll redraw this as having a short circuit, and we will be looking from this side to calculate the R equivalent. So let me redraw it. So alternative method, per R equivalent is equals to RTH. Okay, so the first step was 0 the independent source, right? And voltage across short is 0, so we sort the voltage source. We'll then get something like this. We have, so there was the voltage source that is now short circuited. Sorry, this was 20 ohm. This is 8 ohm. This is 12 ohm. And R equivalent is looking from this perspective. Right, so if you're looking from this side, so the current is moving from point A to point B, current goes here, but then it divides between this side and this side. So these two sides are in parallel, but then they join at some point. So the current, the R equivalent will basically be, so these R it goes towards 5 and 12, which are in parallel, but ultimately this circuit is in parallel with 12, so that is in parallel with the 12 ohm resistor, right? That will give us 8 plus 5 times 20 divided by 25, which is 4, and that is in parallel with 12. So 12 parallel 12 is 6 ohm, which is the value we obtained here. So they match. So that's how we verify the resistance obtained. So finally we have to sketch the Thevenin Norton equivalent circuit to get the answer. So let's finally sketch the Thevenin and Norton equivalent circuits. Okay, let's write Thevenin on this side and Norton on this side. So RTH is equals to 6 ohm, and we calculate the VOC, which is VTH, is equals to 64.8 volt. This was between point A and B. That is the Thevenin equivalent, and Norton equivalent will be A. We have a current source, B, and a parallel resistor. So Rn is equals to RTH is equals to 6 ohm, and IN is equals to the short circuit current, not 6, 10.8 ampere. So that was the short circuit. So this lecture is going to be longer than I expected. I'm going to include the case where we can find the equivalent circuits when there are dependent sources. So let's see this special case. Finding Thevenin and Norton equivalent when the circuits contain dependent sources. Okay, these two conditions still apply. VTH is equals to VOC, IN is equals to ISC, and then we can also calculate RTH is equals to RN is VOC divided by ISC. So these still apply. The only problem is when you are trying to find the R equivalent using alternative method by zeroing the sources. So we'll have to revise that method. So we'll revise that. Okay. Okay, alter. Alternative method for finding resistance, and this one is a revised method. Okay, so as with the earlier case, we deactivate the independent source. Deactivate the independent. We deactivate the independent sources if they have multiple sources, and then we apply a test voltage or test current source to the one port network. So we apply a test voltage source or test current source to the one port network. Okay, and after that we can calculate RTH is equals to RN is equals to R equivalent is the ratio of the test voltage divided by the test current, that is calculated based on the test voltage. Okay, this might be confusing, so we'll just start with an example and that will clear up things. Here again we are asked to find the Thevenin equivalent. Thevenin equivalent. And the circuit here is, we have a dependent source, that is the problem. Minus plus, this is 2Vx so here is the open circuit, this is 2 ohms, we have another resistance here, which is 6 ohms, you have 2 ohms here, and this one is 4 ohms, and the voltage, that is this voltage source, is dependent on the voltage across here, which is Vx. Okay, so this is 4 ohm. So this is the problem, and looks like we have in here, we have a practical current source, right? Let me write the value of this source, 5 ampere. Okay, so you might be tempted to do source transformation, but whenever we have a dependent variable, a dependent voltage source or current source, we cannot do source transformation. So that is something we need to be careful about, and we need to find the circuit voltage, open circuit voltage. So what would be a good method to do in this case? As usual, you can see that we can do node voltage here. Okay, but before we start with that, we have to look into something that we discussed over last 2 weeks, last 2 lectures. So this part of the circuit here, the one highlighted in yellow, so this is a dependent voltage source in parallel with resistance, and if you remember, this is called a super node, right? Super node. So every time we have super node, we can do KCL at super node and KVL super node to solve for problems. So let's do the node voltage method and see what are the unknown voltages here. Okay, so since this is open volt source, we have I is equals to 0 here. We have 4 nodes, and if we consider this as the ground, V reference is equals to 0. This voltage, this current here will be 5, right? So this will be same, and the only unknowns are this, which we can call as Vx, and one is here. And since the current across open circuit is 0, we can assume that there is negligible voltage drop here, and then this will be VOC, right? And we can randomly assign current directions to solve for KCL. So we can write this and this, and we can write plus minus plus minus. Okay, so that should be enough to do node voltage here. Let's start by writing KCL at super node. So the current entering the super node is 5 ampere, right? This source current, and the current leaving is this, which can be written as Vx minus 0 divided by 4, right, in terms of voltage across the nodes. And the other current leaving the super node is this, right, because this current is 0. And this current across 6 ohm resistor can be written as VOC minus 0 divided by 6. So basically write that equation here, 5 is equals to Vx divided by 4 plus VOC divided by 6, right? And if we simplify this, we'll get 3Vx plus 2 VOC is equals to 60. So that will be our first equation. And every time we apply KCL at supernode, we also have to apply KVL at supernode. So we'll write KVL at supernode. And if you look into the supernode, since this side is positive, VOC minus Vx will equal to 2Vx, right? That's the KVL around the supernode, right? So VOC minus Vx is equals to 2Vx, or 3Vx is equals to VOC. And if we put 3Vx is equals to VOC in this equation here, we will get VOC plus 2VOC is equals to 60, or basically solving 1 and 2 will get 3VOC is equals to 60. Therefore VOC is equals to 20 volt, and then Vx will be divided by 3, so 20 divided by 3 volts. Okay, now for resistance we can use the alternative method here. Okay, so remember the steps. Let's write this: alternative method per resistance. So the step 1 was deactivating the independent sources. So let's deactivate the independent source. And we know that whenever we have current source, we open circuit it, and whenever we have voltage source, we short circuit it. In this example, we have a current source, so we'll just do open circuit it here, and then everything else remains the same. Okay, let's do that. Let me redraw the circuit. This is 2Vx. Okay, so this was our one port terminal. Let me insert the resistance here. So there was one resistance here which was 2 ohm, right? So this is 2 ohms, this is 6 ohms, this one was 2 ohms, and this one was 4 ohms, and the voltage across this was Vx. That's why this source, dependent voltage source, is dependent over there. And so now we have open circuited this one. What next? Can we deactivate the dependent source? We can't. And whenever we have dependent source, the step 2 was applying test voltage at the one port node. Okay, so we are going to add some voltage here, which we call as test voltage. Okay, so step 2 is apply test voltage. Apply test voltage at one port. Okay, so what we are going to do is let me write it a different pen. So this is our one port, and we are going to apply a test voltage here. So insert a voltage source which we call as B test, and a good value to pick for the test voltage is 1, because then once we start calculating the current, the resistance can be just 1 divided by whatever the value of current is, so it's easy to calculate. So based on this direction, I'll assign the I test as this. Now if we can find I test flowing, we can determine the equivalent resistance, which is basically the ratio between the test voltage V test and the test current I test. And again, since this problem has super node, the easiest way to find the voltage is the super node method, right? So we can apply node voltage method again. So there is our reference node. I call this as reference node, and V reference is equals to 0, right? And this resistance, this voltage Vx is unknown. Similarly, this Vy is unknown. And then we can randomly assign the current direction. So in this case, assign this and this, right? And since this is flowing this direction, we can assign the polarity as this. So we assign the current direction, we assign the unknown voltage. So next step is KCL at supernode, right? KCL at supernode. And remember, this was our supernode. This was our supernode. Whenever we have a dependent voltage source in parallel with the resistor, that is a supernode. And here in KCL at supernode, so the current entering the supernode. What is the current entering the supernode? So that is the difference between this V test minus Vy divided by 2, right? Which is basically I test, written as difference between voltage. That's what we do with the KCL for node voltage method, right? So V test minus Vy divided by 2, which is 1 minus Vy by 2, that is the current entering. And the current leaving is one is Vy minus 0 divided by 6, and the other one is Vx minus 0 divided by 4. Okay, we'll write that down. So KCL at supernode gives 1 minus Vy. This one is actually the value of V test here. So divide by this resistance 2 ohm here, and then that is equals to the current leaving Vx divided by 4 plus Vy divided by 6. If we simplify this, we get 3Vx plus 8Vy is equals to 6 as first equation. Every time we apply KCL at supernode, remember we have to apply KVL at supernode. So KVL at supernode. So just by looking into this circuit, we have positive terminal this side. So Vy minus Vx should be equal to 2Vx, right? So that's the KVL. Vy minus Vx is equals to 2Vx, or Vy minus 3Vx is equals to 0. So now we have two equations, two unknowns we can solve, and that will give us Vy is equals to 2 by 3 volt, right? And then we can calculate the I test, which was again voltage drop across here, V test 1 minus Vy divided by 2, and we already calculated Vy, so 1 minus Vy divided by 2, that will give us 1 by 6 ampere. And since we know the I test and V test, then our equivalent is going to be V test divided by I test is equals to 1 divided by 1 by 6, which will give 6 amperes. 6 ohms. 6 ohms. Okay. So finally we can draw the Thevenin equivalent circuit. Okay. So the Thevenin equivalent circuit will be will be like this. I have a voltage plus minus, the VTH is given as the volt that we calculated earlier. Here we open circuit, this is the Thevenin voltage, right? VTH is equals to VOC. So that is 20 volt, and RTH is something that we just calculated here, 6 ohms. So this is the Thevenin equivalent circuit. With that, we are done for the day. In next class, we will look into maximum power and superposition, and I will see you in class. Thank you.